To finish this class, let us quickly review the exponential and the logarithmic functions. Let's start off with the exponential function. An exponential function is always of the form f of x is a to the power of x, where base a is always a positive constant. Remark, this is different from the power function, because a power function is x to the power a. So x is the base number and we have a constant power. For an exponential function, x is always in the power and we have a constant base. So if a is a positive constant, so if a is strictly larger than 0, then we know that a to the power 0 is 1, always, because to the power 0 is 1. And a to the power n is just a times a times a and so on times a, in total n times. This holds for n is 1, 2, 3, and so on, so for n a natural number. We can also extend to the integer numbers by saying that a to the power minus n is 1 divided by a to the power n. For n is 1, 2, 3. So basically here we have defined all the natural numbers. Here we have defined the integer numbers. And then next we will define the rational numbers. So a to the power m over n is just a to the power m and then the nth root out of this value, where n is 1, 2, 3 and so on. So n is positive and m can be positive or negative. So we have defined natural numbers as powers, integer powers and rational numbers as powers. But what if the power is not rational? What if x is not rational? If x is not rational, so if the power is not rational, what we then do is we use limits. For example, if we have a to the power x and x is a real number, so not a rational number, then we will say a to the power x is the limit of r going to x of a to the power r, where r is a rational number. So we will go to powers of rational numbers, but with rational numbers that have a limit of x. For example, a to the power pi. Pi is a not rational number, so we cannot write it as a fraction of two integers. What we could do is we could take the following sequence. R is 3, r is 3.1, r is 3.14, r is 3.141, and so on, in such a sequence that r converges to pi. Let's plug in a equal to 2, so 2 to the power pi. What you then see is the first one will be 8, the second one will be 8.574, and so on. And then you can write that 2 to the power pi is the limit of 2 to the power r for r going to pi. And then if you can calculate this, you use a computer or you use a calculator. This gives you 8.824 and so on. What does the graph of an exponential look like? There you make a distinction between the value of a. If the value of a is larger than 1, then you see that you have an increasing function with the limit at minus infinity going to 0 and the limit at plus infinity going to plus infinity. If, on the other hand, the base a is between 0 and 1, then you will have a decreasing function where the limit at minus infinity will be plus infinity, the limit at plus infinity will become 0. What are the laws for exponentials? So first of all, a to the power 0 is always 1. A to the power minus x is 1 divided by a to the power x. A to the power x plus y becomes a multiplication, a to the power x times a to the power y. And similarly, a to the power x minus y is a to the power x divided by a to the power y. Furthermore, if we have a to the power x to the power y, this is just a to the power x times y. And if we have a times b to the power x, this is a to the power x times b to the power x. And then finally, for the exponentials, there is one special case. For this, we need to know Euler's number, which you probably know from high school. Euler's number is indicated by the letter E and is defined as the limit of 1 plus h to the power 1 divided by h for h going to 0. And it has a value of approximately 2.7. If we take e as base, then we get a special logarithmic function. So in that case, we write f of x is e to the power x, or also exp of x. And we say this is the exponential function. So we do not define a base. We do not define the base a. If we just say it's the exponential function, then this means that the base is Euler's number. So you know that e is the limit of h going to 0 for 1 plus h to the power 1 over h. If we rewrite this expression, you can also say it's the limit for n towards infinity of 1 plus 1 divided by n to the power n. So what we just did is here set h is 1 divided by n. So if h goes to 0, then n is 1 over h, and n will go to infinity. With this last formula, you can also define powers of e. So e to the power a is just the limit for n going to infinity of 1 plus a divided by n to the power n. So here e to the power a means that in this case you write an a instead of a 1. We can easily prove the formula. So start from the formula e to the power a is the limit of 1 plus a divided by n to the power n, and then n to infinity. What we do is set a divided by n equal to 1 divided by x. Then we know if n goes to infinity, this also means that x is n divided by a, so this will also go to infinity. And so the limit becomes the limit for x to infinity, 1 plus 1 divided by x, and then the power n just becomes a times x. If we rewrite this, you get the limit x to infinity, 1 plus 1 over x to the power x, and then this to the power a. We then know we can take a limit inside a power, so it's the limit of 1 plus 1 over x to the power x, and then this limit to the power a. And now we know that this limit here, this is just e because of the definition, e to the power a, and so we've shown that the formula is correct. And then finally there's the logarithmic function. The logarithmic function is just the inverse function of the exponential. And so the way to define it is also through the exponential. So a logarithm of x with base a is y if and only if a to the power y is equal to x, under the conditions that a is strictly larger than 0 and a is different from 1. So the way to say it, this is log of x to base a. Because a logarithm and the exponential are each other's inverse, we can write, or we know that the logarithm to base a of a to the power x is x for each value of x, and also that a to the power log of x, if we have a logarithm with base a, is equal to x for every x. So they are each other's inverse, they cancel each other out. The laws of a logarithmic function, they are directly linked to the laws of the exponential function. So the logarithm of 1, no matter which base, is always equal to 0. The logarithm of a product is a sum of logarithms. The logarithm of a division will be a subtraction of logarithms. Then also you have a power rule. So if you have a logarithm of x to the power r, this is just r times the logarithm of x. So you can take out the power as a multiplication. And then there is one more important law. It says that the logarithm of x to base a is the logarithm of x to base b divided by the logarithm of a to base b. So this formula allows us to change the base, so to replace a base where we cannot work with by a calculation with a base that's easier to work with to find a solution to a problem. The graphs of the logarithm are the inverse of the graphs of the exponential. So again, you make a distinction. First of all, you take a, the base a, strictly larger than 1, and then you have an increasing function. If the base a is between 0 and 1, you will get a decreasing function. And then finally, the special case. The special case is linked to the exponential, to Euler's number, so we call that the natural logarithm. So ln of x, we write the natural logarithm as ln. Ln of x is just the logarithm of x to base e.